Hi, William. I'm very pleased to introduce William Lamb to you. He's from the Vanderbilt University in Nashville, Tennessee. Very exciting topic. I must say, I know absolutely nothing about this, William. I'm very excited to hear this. I'm sure all the attendees today too. So I'm going to hand it over to you. Welcome to iTelescope.
Yeah, thanks, Christian. Thank you very much for inviting me. I'm very excited to share this experiment and these results with you today. I'll just share my screen now.
Very good. We can see it. Beautiful. Yeah.
Excellent.
Yeah.
Can you see it in like the full screen view?
Yes, I can. Everything's fine. Go
Lovely.
ahead. Yeah.
Okay, so today I'll be talking about unlocking some cosmic mysteries using the NANOGrav pulsar timing array experiment. But yeah, my name is William Lamb. I'm a fourth year PhD student at Vanderbilt University in Nashville, Tennessee, in the USA. I thought, first of all, though, I'll just talk a little bit about who I am. I'm originally from Wales in the UK, up in Eryri or the Snowdonia area. And I'm from a village of about 100 people called Penisa'r-Waun. We're all Welsh speakers there, and I grew up amongst sheep and all the castles and all the mountains, and it was just a wonderful place to grow up. But that's where I first started my love for astronomy, because we're also in a dark sky reserve, so we got to see some wonderful dark skies over there. I then went to do my undergrad at the University of York in northeast of England, where I was representing the Institute of Physics as well. Also a beautiful city, lots of great hiking spots. Loved the tea there as well. And it's where I first started to learn swing dancing as well, which has become one of my favorite hobbies. You can see me over here in the right corner. And now I've moved to Nashville, Tennessee. A lot of people ask me why, and I grew up listening to country music. So Nashville is the like the home of country music essentially. But yeah, I live there with my partner now, and our cats. And we have plenty of kittens around as well. Still dance. Sometimes I get to do a little bit of work as well if I have the time. So yeah, I'm also a writer for a website called Astrobytes. I know that quite a lot of speakers for iTelescope come from the Astrobytes collaboration, so I'm sure you know what it is. But a lot of this presentation is inspired by this first Astrobyte that I wrote nearly a year ago now, about counting supermassive black hole binaries at coffee shops. So in this talk, I'm going to cover a little bit about supermassive black hole binaries and introduce gravitational waves, although it sounds like you know quite a lot about them already. And then I'll go over what a pulsar timing array is and how they work and why we use them, and then just why these results are important. Okay, so start off, what is gravity? We grew up in school learning Newton's equations, so gravity is a force between objects. But when we get into these highly energetic regimes, truly massive objects or really fast accelerations, this theory doesn't quite work. There are some deviations between theory and observations. So Einstein came along and put forward that gravity isn't a force, but actually a curvature in space. And space tells how mass to move, and move tells space how to curve. And the logical endpoint of this idea that mass causes space to curve is that if you put a lot of mass into a really, really small area, you'll get to a point where the curvature is so great that not even light can escape. It's impossible for anything to go faster than the speed of light, but you need to go faster than the speed of light to escape these regions of space, and this is where we get black holes. And a black hole is, this region of space that you cannot enter. Nothing can come out. Well, sorry, you can enter the black hole, but you can't come out of it. You can't get any information about the inside of the black hole from the outside. So this event horizon is this boundary where you can't get anything out of it anymore. And then the singularity is like the point where all the physics just completely breaks down and we don't know what it is. But yeah, just to give you an idea of the sizes of black holes, this is a city map of Nashville. And if you took the sun and turned it into a black hole, this is how big it is. It would be less than 2 miles in radius. So to go from this area, which is the football stadium, the American football stadium, not proper football, to go from the stadium to one of my favorite bars in town is nearly 2 miles, and it takes like 10-minute cycle ride. You can cycle from the center of the black hole to its boundary in 10 minutes, like if you could. But these are really small objects. You probably saw the photos from the Event Horizon telescope a couple of years ago, photographing the black holes at the center of M87 and our Milky Way. I've just got this little zoom bar in the way. I'm just going to move that out of the way. So the black hole at the center of our galaxy, the Milky Way, Sagittarius A star, has the same mass as 4 million suns, but it's so small that it would fit within the orbit of Mercury, which is it's pretty crazy. Just think like how much mass is in such a small area. Compare that to M87 star, which is nearly 1,000 times more massive. It's still about the same size as our solar system. So these are really, really small objects, but because of our technology now, that we can actually start imaging them, even though they're extremely far away. And sometimes these black holes get close to each other and start to orbit each other and form a binary. They'll start just forming this little binary system that start orbiting around each other. And this is where some really cool physics start to happen. So in this animation, you can see a lot of gravitational lensing. So the light from the gas disk surrounding the black hole, they just start to warp, especially when one black hole comes in front of the other. So we can start testing the limits of general relativity, Einstein's theory, using these binaries. But the way that I test general relativity is by using gravitational waves, which you can see like a little hint of in this image in the top right here. So what are gravitational waves? So black holes create these really deep wells in space-time, essentially. So when they start orbiting around each other, those wells are moving extremely quickly and just generate these ripples in space that radiate from the binary. You can see in this left-hand animation over here, you'll see these ripples in space and time, not in time, just in space, coming from this binary. So if you had a ring of, say, planets, and a wave comes through the screen, you'll see the wave deforming that ring in either a plus or a cross pattern, as you can see in the top right. So that's how these waves work. But as with all waves, it's just good to remember they all have an amplitude or, say, a power. They'll have a wavelength, which is just like the length between peaks in the wave, and then a frequency, which is like the number of oscillations or the number of waves that pass through a region of space every second. So we expect to see these black hole binaries all over our universe, because why not? So that means, let's say if we compare it to a cafe now, it's like having couples enjoying some coffee or some brunch in a cafe, throughout a cafe. And all of these couples are talking. They're given off gravitational waves. So you have this cacophony of gravitational waves coming from across the universe. But if we want to start learning anything about these binaries, then we need to start listening to these voices. But how do you separate out these voices and start learning about these binaries? So for example, you might have these short bursts of really loud waves that are really high pitched. Say like there's a baby somewhere just screaming, and a parent just trying to calm them down. Or in another corner, you might have some, let's say, some older actors like Michael Caine and Morgan Freeman just talking in their really deep voices for a long time and just really enjoying themselves and staying there for a long time and just talking for a long time. And that's what we expect from the spectrum of the gravitational waves, from all these binaries across the universe. The spectrum is kind of like how you just separate light in white light using a prism into the rainbow that you see. So you'd get the low frequency red up to the higher frequency blue light, and you also go beyond that. Gravitational waves also have a spectrum. You'll have these higher frequency gravitational waves, which you can see with LIGO, and then you'll see these lower frequency gravitation. We expect to see these lower frequency gravitational waves as well, which I'll go into later. So these high frequency gravitational waves, it sounds like you've covered quite extensively. They're caused by solar mass black hole binaries or neutron star binaries or black holes and neutron stars orbiting around each other and merging. And you'll see this merger happen in experiments like LIGO, which was based in Livingston and Hanford in the US. And you also have the Virgo in Italy and the new Kagura experiment in Japan. So yeah, these high frequency gravitational waves are kind of characteristics as seeing these compact objects merging, creating this little chirp of gravitational waves. And I'm sure you've all heard that and seen it before. But these are kind of like those screaming babies that you'll see just like overwhelming the cafe. The low frequency gravitational waves up to this year we hadn't actually detected, but we expected them to be there, and they would be caused by supermassive black hole binaries. So these are different to those solar mass black hole binaries because these binaries that create the low frequency gravitational waves have masses of greater than 1 billion suns. And we would expect these at the centers of galaxies. And because these are so massive, the gravitational waves that they would generate would be a little bit would be stronger. So that's why we can see them at these lower frequencies, which correspond to a bigger distance between these black hole binaries. And we'd expect to see a lot of them across our universe. So instead of seeing one like blip, we expect to see these binaries orbiting around each other for a long, long time, generating gravitational waves. And like voices in a cafe, they talk over each other. So instead of hearing one voice, we hear hundreds of voices, and they create a background signal. And from that loudness, we expect to be able to count the number of supermassive black holes, binaries there are in the universe. So I briefly mentioned that these supermassive black hole binaries are a result of galaxy mergers. So we believe that galaxies that we see in our universe are the result of many, many mergers over time, which you can see, for example, in this photograph, which I believe is from Hubble. So galaxies form by just all of these mergers going on over time, making bigger and bigger galaxies. So that suggests that the black holes at the center of each of these merging galaxies will fall into the centers of the new galaxy that they form, orbit around each other, and maybe eventually merge into a single black hole. Every galaxy pretty much that we see nowadays have single black holes in them. So just quick question, just see how everyone's doing. So when a supermassive black hole binary radiates gravitational waves, what happens to the distance between those binaries? Does it A, increase, B, decrease, or C, does it stay the same? I'll give everyone a minute just to answer that.
Yeah, you've really done it beautifully. Beautiful explanation. Just think of the word merger, then you'll know the answer.
I've kind of given you plenty of hints along the way.
Yes, you have. You have. I like the analogy, by the way, of the screaming baby. I think I would prefer to listen to a merger rather than a screaming baby.
Yeah, the mergers sound a lot nicer. It's just a little chirps.
Yeah, and just it was also very funny. But whilst they're doing this, your analogy on saying that real football, in Nashville, this is American football. In Europe, we play real football. I love that one.
Yep.
So, okay, we'll give
Funny
them.
enough, I'm not actually a fan of either, so
Well, there you
it's
go.
fine.
I'm neither am I either. But I was just a quick comment on you in Wales, because I mean, when I was in Wales, I remember we had this beautiful clear sky, but really a few minutes later it would be cloudy and would be raining. So I'm
Yeah.
really impressed that you became interested in astronomy in Wales. I think you have
Yeah, I
something.
was just lucky to just be there all the time. So like you might get 2 months of no clear skies and then one night it would just be magical. So
Yeah, and I think it has something around 2,500 milliliters of rain per year, if I remember correctly, somewhere around there, right? It's a lot. Anyway,
yeah.
I'll be quiet now. Let's.
So yeah, the answer is that distance between the binary will decrease because the gravitational waves carry away energy, they carry away the angular momentum from that binary. So that binary starts to the distance between the black holes will start to decrease, and eventually they should merge, or will they? So if we take Einstein's theory, um, and calculate how fast these binaries should merge over time, we expect that merger timescale to be longer than the age of the universe. But we see single black holes at the centers of galaxies. So something's wrong. Either Einstein's theory is wrong, or this idea that galaxies build up from many mergers over time is incorrect, or we're missing something. So questions are, what happens during the inspiral, and why doesn't the theory say they would merge? Uh, and this was a difficult problem for a while because we cannot resolve the binaries in these faraway galaxies using traditional telescopes because they're just too far away and these binaries are too close together and the centers of these galaxies are too bright. So what are we going to do? Well, we have the gravitational waves from these binaries, so we need to find a way to listen in to them. Okay, so second question now. When a gravitational wave passes by between two objects, what happens to those objects? Does the mass of the objects change, or the distance between the objects change, or does the density of the objects change? People got it correct. It's like the distance between the objects will change. So if you imagine like a wave passing through a pool, it oscillates whatever is in that pool. So show this with this small animation down here. So we've got the Earth here, and we have a pulsar over here. The observed distance between the Earth and the pulsar will change. The pulsar will move back and forward when a gravitational wave passes through. So that brings me nicely onto what are pulsars. So pulsars are these extremely compact objects, the type of neutron star that rotate extremely quickly. The fastest pulsars, millisecond pulsars, rotate faster than a kitchen blender, approximately like once every 1,000 seconds. And they have these really strong magnetic fields, and they radiate beams of radio waves from their magnetic poles. But the axis of rotation is offset from the beams. So when the pulsar rotates, these beams sometimes sweep across the direction of the Earth. And what we'll see is a pulse, hence pulsing star or pulsar. And because these pulsars rotate so quickly and they have such high masses, their rotation is extremely stable. We can use them like stop clocks. In fact, back in the 70s, I think they were even used as like the standard clocks because it was just so accurate. You can predict when a certain pulse will arrive at the Earth 10 years in advance. They're just so precise. They were first discovered by a graduate student back in the 60s called Jocelyn Bell Burnell. She called the first pulsar LGM1, which meant Little Green Men 1, just as a little joke, because you wouldn't expect to see such regular pulses in the night sky. In the end, it was called, I think it was like CP1919, and this was the trace plot of those pulses over time that she observed. Quite a few of you might also recognize this as the album cover for Joy Division. Was it Undiscovered Pleasures or something like that? I don't remember. I'm not a big is it 70s 80s music fan, except for Fleetwood Mac. But yeah, I see this plot a lot on t-shirts now. It's fascinating. Okay, so we now have these extremely regular clocks scattered around our Milky Way. So we can now use them to potentially discover gravitational waves. So here we have the Earth, radio dish looking at all these different pulsars, and a gravitational wave passes through. So question 3, this is the last question now. What do you think happens to the pulsar's pulses when a gravitational wave passes by? Do they all the pulses arrive sooner? B, do all the pulses arrive later? C, some will arrive sooner and some will arrive later? Or D, will nothing change? I'll give you a moment for that.
Yeah, very,
Someone
very.
can correct
Sorry.
me on the album name as well.
Yeah, very, very fascinating. This way of detection. It really is incredible.
Yeah, pretty much most people got it correct. Some pulses will arrive sooner and some will arrive later. Great job. So I'll just show this little animation again. So when the wave passes through, this pulsar looks like, from the Earth to be oscillating back and forward. So when it moves forward, all those pulses, well, the pulsar appears closer to us, so there's less distance for the pulses to travel between the pulsar and the Earth. Speed of light is constant, so all that can change really is the time it takes for that pulse to arrive at the Earth. So when it's closer, smaller distance, so the time it takes for the pulse to arrive at the Earth is shorter, so that pulse will arrive earlier. And then opposite direction, when the pulse is further away, there's a longer distance for that pulse to travel to the Earth, so it takes a longer time for that pulse to arrive at the Earth. And so we have these pulses will arrive just a little bit later. These changes are on the order of nanoseconds. They're really, really small because the space in between the Earth and pulsar change is like the change in distance is tiny. But because we have these extremely precise clocks in space, these pulsars, we can actually detect this, which is pretty amazing. Ooh. Can't get on to the next slide. So what is the pulsar timing array? Well, it's essentially just an array of pulsars in our galaxy that we time with the NANOGrav experiment. In the last data set, we were timing 67 pulsars across a galaxy that looks like this, and we're over here. And our galaxy is bathed by these gravitational waves coming from these galaxy mergers that come across the universe. And all these gravitational waves will change the distances between every single pulsar here and the Earth. So essentially what we've built is a galaxy-sized detector to detect all these gravitational waves coming from all directions. So a big question is now, like, how do we actually know that what we're seeing is a gravitational wave or background of gravitational waves, rather than say we've made a mistake in computing where the Earth is compared to the sun, because like the Earth is orbiting around the sun, we're all orbiting around the center of the galaxy, so everything is changing all the time. The way we do this is by computing the correlations between the timing differences between all the pulsars in the sky. It's a little bit complicated, but if you think about old analog TVs, if you put two analog TVs next to each other and you put the antenna in one direction, and in the antenna on the other TV, if you point it in a different direction, one might have better signal compared to the other, just because of the way you're pointing those antennas. Those antennas will have certain sensitivities in certain directions. If you compare the strength between the pickup those two TVs get, you'll get this correlation value. If you change the angle between those TVs, that correlation will change according to a certain function, to a certain thing that we know. It's very similar with pulsars. Essentially, what we have are these antennas, like the pulsar to Earth distance is effectively one antenna, and we have 67 of these antennas because we have 67 pulsars. So if you start comparing all these antennas with each other and compare them, compare like the signal that they pick up from these gravitational waves as a function of the separation between these pulsars in the sky, you should get really nice, what we call the Hellings and Downs pattern. So this little blue curve that you'll see pop up in just a second. Here we go. So this is the signal that we're looking for. This will tell us that we're actually seeing the gravitational waves. And this is the result that the NANOGrav experiment got, and it agrees extremely well. If gravitational waves didn't exist, we would not see this pattern at all. You would just expect zero correlation, like all these data points will just be around this red line. If there were mistakes in our experiment, we'd see different patterns, so like a straight line at 1 or maybe a sinusoid, but no, what we're seeing is this really nice blue curve, which tells us there's a gravitational wave background. So what is NANOGrav? It's the North American Nanohertz Observatory for Gravitational Waves. I am a member of it. This is our data set so far, and we're still collecting more and more data in the coming years. So this is 15 years worth of data. We started back in 2004. I started back in 2020, so I just came in at just the right time for this really exciting result. But we've had different data sets so far, trying to see like how our evidence has grown over the years, and we have so far like the 15-year data set is showing the strongest evidence for gravitational waves, these low frequency gravitational waves. These are our telescopes that we used. So for a long time we used Arecibo, which sadly we don't have anymore. We use a Green Bank telescope in Virginia, West Virginia, yes. Or was it Virginia itself? I don't remember. I haven't been there yet. We have the Chime telescope in British Columbia in Canada, and then the Very Large Array in Nevada. And we're also part of a larger collaboration called the International Pulsar Timing Array. So NANOGrav collects its own data. Then there's also the European Pulsar Timing Array, the Chinese Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, Indian Pulsar Timing Array, and then an upcoming Pulsar Timing Array in Africa called the Meerkat PTA. And on June 29th this year, all those PTAs released their results at exactly the same time with their own independent data sets, and found really strong evidence for these low frequency gravitational waves. And it was really exciting. So my advisor here, Steve, got to go to the National Science Foundation to do this really cool webinar explaining our findings, and he got to sit next to like one of the great heroes of gravitational wave science, Kip Thorne. Jocelyn Bell Burnell was linked in and got to speak for a little bit. We made it onto into front pages of the New York Times, Washington Post, NPR. We were trending on Twitter, or whatever it's called now. I also got onto the front page of the Welsh language BPT service, so that was a really, really cool thing. So why is this important? Well, general relativity is like our best theory for gravity, and so far it's passed every single test. On the flip side, quantum physics is our best theory for all the other forces and all the small stuff, and it's pretty much passing every single test. But when you try and combine those two theories together, they don't play ball. So one of these is wrong. So we need to constantly test these theories just to see like where did things break and what can we learn once we break them. We have this new messenger to learn about a universe. So gravitational waves is a way to carry information from some cosmic object to us, and we can learn a lot of stuff about those objects. We can learn a lot of new physics, and it's pretty cheap because we have these radio telescopes across the Earth already. All you need is a radio telescope and a couple of computers to start analyzing data. You don't need to build these giant machines like CERN, the Large Hadron Collider, which costs millions and millions to run every single year. All of the grad students that work on this project, they start training in data science, and we start developing a lot of techniques for data science as well. And that'll all go out into industry and start improving certain aspects or innovating a lot of things in data science. It's just really cool. Like we've built a galaxy-sized detector to detect gravitational waves from supermassive black hole binaries. It's incredible, just to get your head around. But then you also have this final parsec problem that we're trying to solve. So will supermassive black hole binaries merge? What is going on there? Why is our theory not corresponding to what we observe visually, which are these single black holes at the centers of galaxies when we're expecting binary all the time? So how do we count these binary black holes using our data? So this is what our data kind of looks like. So you have these three pulsars here. If there was no gravitational waves, you would not see any difference in their the deviations in time, like when you expect these pulses to arrive. You'd expect the time to stay constant, so it would follow this gray dashed line. What we see is these timing deviations like wandering above and below these lines. So from that we can then start mapping this background of gravitational waves across our galaxy and try and figure out what are the frequencies and what is the power of these waves that are bathing the Milky Way. And we use something called Fourier decomposition to try and figure this out. So Fourier analysis shows that if you want to take this complicated waveform, you can actually split it up into simpler waveforms. It's actually just created by these simpler waveforms with specific amplitudes and specific frequencies. So all music, for example, like the way you're able to hear me is that the computer takes my voice, it will turn them into these fundamental sine waves. It will just figure out what is the power at each frequency and what frequencies make up this sound wave, and then rebuild it back at your side to turn it into something that you can hear. And this is a really nice compressed way to not just communicate sounds, but also just figure out what frequencies are making up this signal. Because each of these black holes are emitting gravitational waves at a certain frequency. So if we can count like the amount of power that is each of these frequencies, we can start counting the number of binary black holes that are emitting at each frequency. So we have this Fourier transform here. This is just another way to visualize it. You have this really complicated wave signal that you're seeing through your detector. You figure out which frequencies make up that signal. These all add up to make this signal. And then, yeah, you just figure out which frequencies make up that signal and how much power there is at each of these frequencies. And you'll get something that looks like this, power spectral density plot. So you've probably heard of like these white noise, red noise, and blue noise. if we had white noise at all frequencies, you'd expect this plot to be like a straight line, like horizontal line. It means that all frequencies are being emitted equally. So that's why you don't hear like a lot of low noises and you don't hear a lot of high-pitched voices. Specifically, you just hear all frequencies at once. Red noise, however, is characterized by a lot of power at low frequencies and less power at high frequencies. This is why we call it red noise, because if you turn this into light, you get a lot. So red light is low frequency compared to blue frequencies. So you get a lot of red light and not a lot of blue light. So visually, you'd see this as red light, and that's why we call it red noise. But yeah, this is how MP3s work. So if you're at a cafe listening to music, that MP3 is just taking a Fourier transform of real music and then turning it into something that you can hear, and it's just a compressed way to listen to music. So NANOGrav kind of does this Fourier decomposition thing, though it's a little more complicated because our data is not as neat as we would like, just because like the amount of time we can get on telescopes and such. But what we see is this little red noise signal. So these gray violins here is our signal that we're seeing, and then we try and fit a model to those to that real data. So this dashed black line is what you'd expect to see from gravitational waves coming from supermassive black hole binaries from across the universe that slowly inspire into each other. And then this blue line here is the best fit to these violins. So as you can see, they they agree pretty well with each other. This is really strong evidence that supermassive black holes are causing this signal. And the reason for this is because when the black holes are orbiting each other, they're giving off these gravitational waves. You get lower frequency gravitational waves at longer distances between the binaries, but because the binary is longer, like further away from each other, the gravitational waves they emit are weaker. So it takes longer for energy to be removed from the system. So it takes a while for those binaries to slowly merge towards each other. So they spend a lot of time in this low frequency range. So they can emit a lot of gravitational waves at this low frequency range, and that's why there's so much power in this low frequency over here. When they start getting closer to each other, though, they emit high frequencies of gravitational waves. It's still in the nanohertz range, so it's not the same frequency range as you'd see here with LIGO. It's still millions times lower frequency than what you'd hear with LIGO. But because they're giving off stronger gravitational waves, the distance between the binaries decrease faster, so they move out of this frequency range faster, and that's why we see less power at these higher frequencies. So we expect to see this red signal. We can do some more complicated stuff, like taking simulations of galaxy mergers, such as using the Illustris simulations. You get these really pretty simulations that look like this, and figure out what else could be causing this signal, and what signal shapes do we expect to see in our data set. So supermassive black hole binaries are not just merging like in a vacuum, or not just inspiraling just in a vacuum. They have the entire galaxy that has just merged surrounding them. So they're interacting with the gas in the binary and also interacting with other stars in the galaxy as well. That takes away energy from them, and that causes them to merge faster. And this is actually the way to solve this problem. The reason why they can merge within the age of the lifetime of the universe is because they're probably interacting with the rest of the galaxy. We just didn't have evidence for this yet, but if we use these simulations to model these interactions, get these different shapes of spectra that you'd expect, these gravitational waves spectra from this population of binaries from across the universe and try and fit it to our data, we see that this is the plot that we get at the end. The black hole binaries that are emitting gravitational waves that we are detecting are actually close enough to eventually merge within the age of the universe. So using our data, we've been able to confirm this for the first time, that by interacting with the galaxy, these supermassive black hole binaries have another way to lose energy on top of gravitational waves. And because of that, we know that these binaries must merge within the age of the universe. And that's why we see these single black holes at the centers of galaxies rather than binaries in the centers of all galaxies. So that's answered that, we think. But I'll get back to that. There are some caveats. So what does that mean about our cafe? So all of these couples in our cafe, they're probably all weightlifters because they're all very big, hungry. They've consumed these a lot of mass over time. They had what we found in the data. They're all pretty massive as well, from this plot here. And over the course of their dinner, they're going to get closer and closer and closer to the point where they're actually sitting on top of each other. That was the only way I can end that analogy. And yeah, I couldn't think of a different way to end that analogy. But what else? I said there was a couple of caveats to this visualization. So have you ever been to a cafe and there are some really loud people next to you and you can overhear them compared to the rest of your conversation? That's probably true for gravitational waves in the nanohertz frequency as well. There might be a really close galaxy nearby with a binary that is kind of overwhelming our detector in one specific frequency, which is pretty exciting. I'll come back to this later on, but that is something that we've also got to add to our noise models. We haven't detected this yet, but it's possible. You ever been to a cafe and someone drops something and it just completely changes the mood and like the atmosphere of the cafe? Similar things happened at the beginning of the Big Bang. There was a sudden phase transition in the way that the forces worked, and this created a lot of gravitational waves that we should be able to detect with pulsar timing arrays. So that's another signal that we're going to have to search for and add to our analyses. There are other objects or sources of noise. Imagine, say, like a cat just hanging around in a cafe. So there are other new physics phenomena that have not been detected yet, but we believe to be true. For example, like cosmic strings that could be creating these gravitational waves at these frequencies. And then finally, there's a lot of background noise as well that we haven't calibrated for. It's like being in a cafe and just hearing like all the baristas making the coffee, a lot of clinking of cups and such. So in each of these pulsars, there's a lot going on within the pulsar itself, and also between the pulsar and the Earth. There's like a lot of gas and dust that could affect those pulses, and we need to measure that and be able to correct for that. And right now, that is something that needs to improve before we can start saying anything conclusive. So because of this, we can't say right now that the gravitational waves that we're detecting is actually coming from supermassive black hole binaries. It looks like it agrees with it, but all these three different sources as well could also contribute to that signal. And also, if we correct for this, we'd be able to get better measurements as well. If we can correct for the noise within our pulsars, we can get better measurements. So what do the features of pulsar timing arrays look like? So as I was saying, we have those close by galaxies we think that are creating gravitational waves that we could possibly detect within the pulsar timing array. If we can figure out where they're coming from, like the position in the sky, we can then point a telescope at them. So then we're detecting them in both with gravitational waves and with visual light. And we would learn so much about that galaxy. And that would completely revolutionize our ideas of galaxy mergers. And then we need to make these more, we need to do more noise analyses to calibrate our pulsars better. We can start using more complex models of supermassive black hole binaries, or the gravitational waves that come from these binaries, to be able to include all kinds of other effects that we might not have considered yet, like all the different interactions that the binary could do with its host galaxy. And then from that, we'll finally be able to interpret what is creating this background of gravitational waves within our detector. So just to give you an idea, just what these analyses look like. We have to use supercomputers right now. That takes days to a couple of weeks per analysis, depending on the settings, depending on the number of pulsars, and what kind of correlations are you trying to model. So this is really difficult. But what my PhD is looking at is how can we do this within minutes? And so within, like, I can make a cup of tea and I'll get some results. And I've developed some code for this that I call Keffel. The reason I call it Keffel is because this method uses something that we've called the generalized factorized likelihood, or GFL. Kind of sounds like Keffel, which is a Welsh word for a horse. Horses are fast. Yeah, it was a stretch, but it was fun. And it's starting to be used by our community to start measuring the power in the gravitational wave background that we're seeing, and start fitting all of their different models that could create this background, so that anyone in the future can count supermassive black holes from a cafe. So thank you for listening. Any questions?